Greetings, Paladins. This is Dr. Augustine, and I hope you're all doing well. So for this video today, we're going to pick up on the last two sections of our textbook, Thermodynamics and Equilibrium, and Changing K with Changing Temperatures. I'm actually going to spend far and away the most time on this. This is going to be a pretty quick video. I don't think there's a need to spend a ton of time on this, but I do want to just complete the chapter for chapter 14. If you recall, we said that the big question we're asking in chapters 14 through 16 is, what is left over after a reaction occurs? This first chapter, chapter 14, is just an introduction to equilibrium. And this video, if we look at our periodic table and we look at the equations we've had, remember the blue equation was one you would have had in Gen Chem 1, the Rydberg equation. All the yellow ones are ones we've already discovered, the integrated rate laws, the Gibbs-Helmholtz equation, the delta, our book has delta E equals Q plus W, and then this was from the last chapter, the two-point Arrhenius equation. So this lecture, we're going to see one more equation is going to be introduced to us relating delta G and the equilibrium constant. All right, so let's start by thinking about how we've written some equations down. So we'll take an equation we've used a few times. It's a gas system that's in equilibrium. N2O4 is a clear gas if you look at it. NO2 is sort of a brownish colored gas. It's one of the components in smog. If you look at like in a city and you look at it, you'll see the brownish gas is NO2. This is actually an equilibrium reaction. And you might recall from the last chapter, we often did things like we wrote down the delta H values for these equations. You might remember from the last lecture, we said that if one of the principles of Le Chatelier's principle is you can use the delta H to help predict which way a reaction is going to go. So we can think of this positive 57 kilojoules as like adding heat to the reaction. We could rewrite this reaction this way. Heat plus N2O4 yields NO2. Remember, it's endothermic, so we're having to put heat into the system. So the heat we can treat as being like a reactant. And so what we said when we talked about Le Chatelier's principle was, what happens if we increase the temperature? So if we increase temperature, that's like putting additional heat into the system, and that is going to shift the reaction from the N2O4 side to the NO2 side. So Le Chatelier's principle suggested to us that we can look at whether a reaction is endothermic or exothermic based on the delta H value, and we can predict which way the reaction is going to go. So this principle we talked about in the last section of the book, dealing with Le Chatelier's principle. But this also tells us something else. This tells us that somehow this balanced equation, this equilibrium expression, is somehow related to delta H, which also tells us that equilibrium is related to thermodynamics. Okay, so this is an important idea. This is what we're going to deal with in this chapter. And it turns out the relationship between the thermodynamic quantities and K is given by the following expression. Delta G reaction is equal to delta G naught reaction. Remember, this is the standard condition, plus RT ln K, or ln Q. So this would be the quantity you would want to use to find delta G under any conditions. Let me write that down. This is under any conditions. And you note that we're using Q here to find this. If we were just interested in standard conditions, let's think about that. Under standard conditions only, remember one of the properties of standard conditions is 1 molar concentration? So that means if we had some reaction like AA plus BB yields CC plus DD, and we were to write what Q is for this, we would say that is C raised to the little c power, capital D raised to the little d power, capital A raised to the little a power, capital B raised to the little b power. But remember, if these are all 1 molar concentrations, this would be 1 times 1 times 1 times 1. So that's all going to equal to 1. So under standard conditions, delta G reaction is going to equal to delta G not reaction plus RT ln times 1, which means this whole term goes to 0, and we get delta G reaction is equal to delta G not reaction. Only true under standard conditions. Okay, but this also suggests something else to us. Think about what's happening at equilibrium. Remember, Q is equal to K at equilibrium. And also, delta G reaction is equal to 0 at equilibrium. These are both true at equilibrium. We talked about that in the last chapter. So if we rewrite this with the equilibrium conditions, now we've got delta G reaction equals delta G reaction plus RT ln K, but now we know this whole thing is equal to 0 because delta G reaction is equal to 0 at equilibrium. So therefore this expression is going to be equal to 0. So let's rewrite this and solve in terms of delta G reaction. Delta G naught reaction is equal to minus RT ln K. Okay, so there's our equation that's on the front of the periodic table. So this equation allows us to relate the standard Gibbs free energy with the equilibrium expression. This allows us to relate those things. What it also allows us to do is we can find K or we can find delta G depending on which piece of information we have. So if we have K, we can find delta G. If we want to find delta G, we just need to manipulate this equation a little bit. So what we're going to do is I'm going to actually now say what happens if we want to find K instead of delta G. So find K, we're going to move things around a little bit. Delta G reaction divided by negative RT is equal to the ln of K. And if we want to solve for K, remember we got to take E to both sides of this equation. And so that's going to give us K is equal to E to the minus delta G reaction divided by RT. By the way, as before, R is 8.314 joule per Kelvin mole. T is going to be in Kelvin. And delta G, if you recall, is often in kilojoules per mole. So just something to be aware of. This is in joules, this is in kilojoules. You're going to have to get these into consistent units in order to do this equation. The second thing I want you to note is this is in an exponential. So a small change in temperature, big change in K. Small change in delta G, big change in K. Remember the lab you did where you had an exponential in the activation energy, and we saw a small change in temperature resulted in a big change in the rate. So this is the same idea. Little change in delta G is going to result in a big change in K. All right, a couple of other points I want to make since we've got this here. First of all, you remember when talking about delta G, we said a few chapters ago, if delta G is less than 0, it's spontaneous. If delta G is equal to 0, it's at equilibrium. And if delta G is greater than 0, it's non-spontaneous. Well, if you look at this expression right here, we have a negative sign out front here to take into this account. Remember, we also said if K is greater than 1, it's favorable for the products. If K is less than 1, it's favorable for the reactants. And the reason for this is K is written as a ratio between products divided by reactants. So remember we said if the numerator is big, you're going to end up with K being greater than 1, and it's going to favor the products. If the numerator is small compared to the denominator, we're going to be favoring reactants. Well, that's what this equation is giving us. If K is greater than 1, ln of K is going to be greater than 1. This is going to be a negative sign. It's going to give us a negative delta G value, which is spontaneous. And if K is less than 1, we're going to get a number less than 1 here for ln. That's a negative number. The negative is going to multiply by the negative. We're going to give us a positive number, which means delta G reaction is going to be non-spontaneous. It's going to tell us that it's non-spontaneous. So these things are all related to each other. You know, we talked about using delta G as our factor to determine whether nature wants a reaction to occur. Well, we can also use K to give us the same piece of information. Now, it's even a little more dramatic than that. This is a plot of the extent of reaction. This is a particular set of conditions for this same reaction we were talking about here. What they have plotted on this axis is the partial pressure of N2O4, the partial pressure of NO2, and delta G reaction in kilojoules. And you can see wherever delta G crosses the 0 point, that's the equilibrium position. Now, here's something else to note. So this band here from like minus 10 kilojoules per mole to plus 10 kilojoules per mole, that's the region where there's like some reasonable probability of finding reactants and products in the mixture. But do you see what happens with this curve? This, because it's an exponential, rapidly increases or rapidly decreases depending on which side of the curve you're on. And this is saying if we get down to like negative 20 kilojoules per mole, there's basically no N2O4. If we get to plus 20 kilojoules per mole, there's basically 0 NO2. So do you see what this is saying? Once we get to delta Gs that are plus or minus 20 kilojoules per mole, the reaction is either all the way on the reactant side or all the way on the product side. So if you remember, when we were talking about delta G a couple chapters ago, we said that it's pretty common delta G is something like 40, 50 kilojoules per mole. So that's telling you the reaction is heavily favored in one direction or the other. If it's negative 40, it tells you it's heavily favored towards the products. If it's positive 40, that tells you it's heavily favored towards the reactant side. It's only in this regime here from like minus 10 to plus 10 that you have an appreciable amount of reactants and products. Your textbook uses a little bit different illustration, but it's showing the same idea basically, and that is for K much greater than 1, if you start with initial concentrations, you're going to end up with very little of whatever this green product is. Remember, much greater than 1 means delta G is very negative, and it's very favorable to form the products. If you have a Kp that's much less than 1, that means its delta G is a positive number, non-spontaneous, and at the end of the day, you're going to end up with very little reactants left over in the chamber. However, if Kp is close to 1, and we start out with a mixture, we're going to still end up with a mixture. If it's a little bit greater than 1, it's going to be a negative delta G. If it's a little bit less than 1, it's going to be a positive delta G, but we're still going to have a mixture of reactants and products. All right, the last thing we're going to do is we're going to take a look at a problem, and I'm going to write out the example here. All right, let's take a look at a problem here. Let's pretend we have our favorite reaction, nitrogen plus hydrogen forming ammonia gas. And let's pretend that we're given the standard Gibbs free energy of this as being negative 33.2 kilojoules for this reaction. And let's pretend we're given the Kp value. Kp equals 6.6 times 10 to the 5. 10 to the plus 5, that's a big number. Negative 33 is a big negative number. So it shouldn't surprise you that we'd have a big positive number and a big negative number here. And this is all at 25 degrees C. And then let's also pretend we have some initial pressures that are given to us. The pressure of hydrogen, partial pressure is 0.25 atmospheres. Partial pressure of nitrogen is 0.870 atmospheres. Partial pressure of ammonia is 12.9 atmospheres. So the questions we have are, calculate delta G under these conditions. And notice these are not standard conditions because these are not all 1 atmosphere pressure. And then the second thing is to predict the direction of the reaction. So I'm going to let you stop the video here for a second if you want to try working on this. But the first thing I'm going to work on is calculating delta G under these conditions. So delta G, remember, is equal to delta G reaction plus RT ln Q for non-standard conditions. And if we look at what we have here, to find Q, that's going to be equal to the partial pressure of NH3 quantity squared divided by the partial pressure of nitrogen times the partial pressure of hydrogen cubed. So that is going to equal to 12.9 squared divided by 0.250 times 0.870, the whole quantity cubed. Delta G for this is going to equal to negative 33.2 kilojoules per mole times 1,000 joules per 1 kilojoule. Why am I doing that? Remember, R is in joules. I'm going to put this in joules. We could do it in both in kilojoules, but they just need to be consistent. All right, so that's my first factor. Plus 8.314 joule per Kelvin mole. Temperature needs to be converted into Kelvin, 298 Kelvin. Kelvin's going to cancel Kelvin. And then this whole Q term is going to get plugged in right here. This will give me negative 33.2 times 10 to the 3 joule per mole plus 23.3 times 10 to the 3 joule per mole. And that delta G is going to equal to minus 9.9 times 10 to the 3 joule per mole. Or we could say 9.9 kilojoules per mole. Negative 9.9 kilojoules per mole. All right, so there's the delta G under these non-standard conditions, 9.9 kilojoules per mole. So what does that tell us? It's a large negative number. Large negative numbers favor products. Okay, so as long as this is a negative number, it's going to be spontaneous in the direction of the products until equilibrium is achieved when delta G is equal to 0. There's a worksheet that's been assigned. Has a whole bunch of different problems involving delta G, the relationship between K and delta G, and I'll let you practice a bunch of more of these. All right, that's going to wrap up the content that you're responsible for in Chapter 14, Introduction to Equilibrium. Next time we will start talking about acid-base equilibrium. I hope you guys are having a great day, and I will talk to you soon. Bye.